Okay, welcome back during the spring break of University of Arizona. Thank you for coming despite being the spring break. So today we have three speakers, and they're all from JWST team. Right, with the, we're gonna hear you. That no, you're not JWST team.
No.
Okay, sorry about that. So we're gonna hear about JWST result, by the way, about teacher. And so first speaker is Naman Bajaj from LPI here, Planetary Science Department, working with Ilaria Pascucci, the third year graduate student.
Second.
Second year graduate student. And second speaker is Andrew Sellek, who received a PhD at University of Cambridge, and then last year, and then moved to Leiden last fall, working with Evina Van Disha. And then the third speaker will be CY, Chengyan Xie, same from LPL, Planetary Science Department, second year graduate student as well. So all three of you, thank you for giving talk today. And then I guess, Naman, you can take the floor.
Hello, everyone. Before I start, I'd like to thank all the organizers for giving us this wonderful opportunity, and particularly Serena for moving around the schedule so much for us. So as Serena mentioned, I am Naman Bajaj, a second year grad student at LPL, just across the street. Not across the street, I'm here right now. And I'm accompanied by Andrew and Chengyan, who are also early career researchers. So today we'll be talking about a very interesting disk called Teacher. We'll take you through our discovery of a spatially resolved disk wind as well as a mid-infrared variability in this disk. And through these three talks, we'll try to convince you that Teacher is really at the end of its disk evolution. Before I move on, I'd like to introduce our team. This is my sincere effort at remaking JWST. And as you might notice, the senior scientists are placed at the bottom half of this telescope, and the early career researchers at the top half. And I think this really echoes with the philosophy of this group, which is to push the early career researchers, help them by giving a solid support at the base. And this newfound telescope is led by, handled by and operated by Dr. Ilaria Pascucci, who is also my PhD advisor, as well as the PI for these observations. This is a truly international effort in a sense that we have people from many different countries working on this project. And we have a really good combination of scientific as well as technical expertise in this group that helped us do all the work. So since I said that I'll be trying to convince you that it is at the end of its evolution, let's talk about the disk evolution itself. So according to the classic picture of protoplanetary disk evolution, in a disk around a young star, the material is slowly consumed via viscous accretion from the inner regions, and the gas in the outer region is dispersed through photoevaporation. Now, in a few million years, the accretion rate falls below the photoevaporative wind mass loss rate, and this can then create a gap in the disk, and the planet can get stuck there. Now, this stage of a protoplanetary disk, where there's a large gap in the dust of the disk, is called a transition disk. And immediately after a few 100,000 years, photoevaporation dominates and quickly disperses all the gas in the disk. Now, this is a very short time period of a few 100,000 years. And this dispersing gas can be traced in ions of noble atoms, such as neon and argon, for the reason that they're available at the surface of the disk, and they do not deplete with time since they are noble. So this is the classic picture that we have. But do we have observational evidence for all of this? The answer obviously is no. More recently, MHD disk winds, or this ejection of material driven by the magnetic field lines of the disk itself, has gained attraction due to its observations. And it is now thought that instead of viscous accretion, MHD disk winds remove the angular momentum from the disk and then drive accretion in the disk. Now, this has led to another interesting thought, that can MHD disk winds drive the dispersal of the disk as well? So, which leads to an important question, that is it photoevaporative winds that are driving the dispersal, or the MHD winds that are doing this job? And to answer this question, we have to, of course, first look at a disk which is at this exact stage of dispersing its disk. So that's what we're trying to do here. And one way to do it is to look at the dispersing gas itself, to observe it, calculate the mass loss. If it's high enough to be consistent with a few 100,000 years, then we are looking at one such disk. And the other way, if you look at it, is you can see that the inner disk also evolves a lot during this short period. So we can also look at that. Now, why do we care about this dispersal? Does it affect planet formation at all? Because it's the last stage anyway. The answer is yes, it does. The wind mass loss rate, it determines how long the gas has, how much time the gas has to be in the system before it leaves completely, which itself determines how long do we have before planet formation and migration will stop. The ionization mechanism, whether it's UVs or X-rays, kind of determines where this gap could be formed is if the photoevaporation is creating these gaps. And then that would determine the planet's location. And of course, as we know, planet's location itself determines the kind of conditions this planet will grow in, the gas it will accrete, and the kind of planet it will form. So this dispersal is really important for these reasons. And I think this is a good time for me to give a little more details about what each one of us will be talking about. So I will be talking about spatially resolving this disk wind, as I said, finding this disk wind, and then Andrew will be showing his models of my observations, and he'll be trying to model them using photoevaporation models to see whether they can explain the observations or not. If they can, great. If they cannot, then we possibly need MHD disk winds to do so. And then Chengyan after that will be talking about the evolution of the inner disk that I was also talking about, that we can see that happens during this short period that we have also discovered through the mid-infrared variability integer. So first things first, let's get right into it. So why is Techa unique? Techa is a T-Tauri star at a distance of about 100 parsec. The age of Techa has a large range in literature, where it's basically older than 2 million years. It has a blue shifted neon to emission, and the blue shift is consistent with a velocity of about 10 to 15 kilometers per second. And this is interesting because this 10 to 15 kilometers per second velocity is consistent with a disk wind, because jets eject at speeds upwards of 100 kilometers per second. So this slow moving gas is exactly what we call as disk winds. So there's already a good signature that neon 2 is tracing a disk wind in this object. The structure of Techa's disk is also very interesting. It has a very small inner disk of size less than 1 AU, a large dust cap of size 25 AU, and then an outer disk of size about 20 to 30 AU, as you can see in the ALMA image here. This is important because photoevaporation in this disk cannot be driven from the inner disk, because it is too deep into the gravitational potential well of the star for the gas to escape. Because photoevaporation can only happen beyond a certain radius, and that is about 1 to 2 AU for a solar mass star. So it cannot happen from the inner disk. And if it's so, this basically means that photoevaporation will have to be radially extended if neon 2 is tracing photoevaporation. And if that is the case, then we should be able to spatially resolve it with JWST. But if you're on the other hand, if you're not able to spatially resolve it, then that would mean that neon 2 is tracing a rather compact gas, which is leaving the system, which would probably be more consistent with MHD disk winds rather than photoevaporative disk winds. So that is the hypothesis here that we'll be working with. Techa has a disk inclination of about 70 degrees, so almost an edge on disk, but not exactly an edge on disk. Techa was observed under the proposal 2260, led by Professor Ilario Pascucci. Techa was observed on August 13-14 of 2022. As I always say, I came to the US on August 11th. The observations happened on August 13-14, and my grad school started on August 15th. So my advisor really made sure I had work to do. The observations lasted for 4.5 hours, and we also observed a dedicated sky background in the exact same settings on the same day, as the sky is particularly bright in this wavelength regime. Techa was observed in the IFU mode, or what we also call as the spectro-imaging mode. That is, we have both spectral as well as spatial information at the same time. So once we had the observations, we had to calibrate them. To calibrate Techa, we individually calibrate the source observations through the JWST pipeline, as well as the background observations through the JWST pipeline. And then once we have the IFU cubes for each of these, we perform a pixel by pixel background subtraction. And then from the subtracted cube, we extract a spectrum. We do it this way because we find that this method of background subtraction works better than all the methods provided in the JWST pipeline itself. And this is what the spectrum for teacher looks like. For the first time, we have not just 1, 2, or 3, but actually 4 forbidden noble gas lines. That is argon 2, argon 3, neon 2, and neon 3. This also is the first detection of argon 3 towards a protoplanetary disk that we know of. Apart from these noble gas lines, we have several PAH emissions, polycyclic aromatic hydrocarbons, which are also excited by high energy photons. And except for all of these, there's only one H2 line and nothing else in the spectrum of teacher, not even silicates, which I think really makes this object interesting, that all we are seeing is a very ionized species. So that was on the spectrum side of things. On the image side of things, what we do is we subtract the continuum from each and every spexel of teacher's IFU cube. To do this, we take every spexel, we plot the spectrum in that spexel, we fit a polynomial to the continuum, and then subtract that continuum to get the continuum free line profiles in each and every spexel. So now we have an IFU cube for lines, an IFU cube for continuum. After this, once we have this line emission maps, we perform PSF subtraction. The idea behind this is, if the line emission is not extended, then it will look exactly like the PSF. So when we subtract the PSF, the end result will just be noise or a zero result. But if we are looking at spatially extended emission, then the emission itself will be a little larger than the PSF. And then when we subtract the PSF, we will have some leftover emission, some extra emission beyond the PSF. So we do this by fitting centroids to both the line emission and the PSF. We shift them to the center, scale the PSF to the line emission, and then subtract the PSF. For the PSF, we use the standard star observation that happened on the same day as teacher. And this is the result that we get from PSF subtraction. So on top left is PSF subtracted continuum at 12.8 micron, that is the neon 2 wavelength. And on right is PSF subtracted neon 2 emission. The contours here are 5 sigma, not 3 sigma. And what you can already see is that it seems that both the continuum and the neon 2 line are spatially extended in teacher. And what is also interesting, if you look closely, is that the continuum is extended more in the direction of east-west, whereas the neon 2 is extended more in the direction of north-south. This is consistent with disk wind, that neon 2 is tracing a gas moving away from the disk perpendicular in a perpendicular direction. And we can see this better when we perform Gaussian fits, which I will not show here, but you can always ask me. In the lower panel here, we have on the left continuums, PSF subtracted continuum at 7 micron, and on the right, PSF subtracted argon 2 emission. As you can see, the continuum at 7 micron may be slightly resolved, but argon 2 is definitely tracing a more compact emission than neon 2. Now that we have 2 lines of each of these atoms, what we can do is we can use the line ratios to investigate what the ionization mechanism is, or which energy photons are ionizing these atoms. So on the left is neon 2 by neon 3 ratio, in red is teacher, and all the other points from literature. And one can already see that almost every point in the literature, along with teacher, excludes the hard UV ionization. And we also exclude the soft UV ionization. As I just mentioned, right, argon 2 is tracing a more compact emission. So it will be very difficult for the soft UV photons to penetrate through this layer of argon and ionize neon further out. So that's why we, since it has a lower penetration depth than the X-rays. So we think the UV is not ionizing neon, but rather X-rays are ionizing neon. And on the right is argon 2 by argon 3 ratio. And the ratio is high enough to suggest that argon is ionized by EUV, which is again consistent with the picture I just mentioned, that argon itself is being ionized by EUV, but it is also blocking EUV to go further out and ionize neon, which is more radially extended than argon. And if we put all these things together in a single picture, then this is a cartoon that we can come up with. So this is a disk of teacher. Here is the small dust disk of teacher with a large dust cap. There's a planet candidate as posed by one of the papers. There's a gas disk, which is much larger than the dust disk. And more importantly, what we find in this paper is that neon is tracing a more radially extended emission coming out of the disk than argon. And at the same time, here I show that UV is ionizing argon, but here I also show that argon layer is blocking UV from penetrating further or going further out. And then X-rays, which can penetrate, are going further out and ionizing neon. So this is the summary for my words of what we have found. And we can look at some of the conclusions right away. One of them is we can use JWST MIRI MRS successfully for these studies, as we have seen that we detected 4 of these lines and one of them was not even seen before. And this study can be used as a pathfinder for all those future studies. The line ratios again are suggesting that neon is being ionized by X-rays while argon is being ionized by UV. And the fact that neon is tracing an spatially extended emission is consistent with both photoevaporative as well as MHD disk-wind scenarios. So we, just based on this observation, cannot really differentiate between the two just now, but that is exactly what Andrew would try to do and tell you more about. And I think a bigger conclusion that we can also maybe make out would be, please give us more time with JWST so we can observe more transition disk and do more of this with more neon and argon lines and see how is it always true that neon is more extended than argon, or they can be at similar spatial distances as well. So next I would hand this over to Andrew, who will be modeling these observations that I just showed with photoevaporation models. Andrew, all yours.
You're muted.
Yep, thank you. Yeah. So thank you for that introduction, Naman. It was really exciting to get to work with you and the rest of the team on this exciting data. The fact that we can see this spatial extension for the first time, and I'm really glad that I had the chance to model some of this and try and actually see what's happening to explain these data. Now, so what is the aim of our modeling, just to restate? Well, we have now the line fluxes that we've seen. We've seen some line ratios, and we also have the extent of the neon and argon emission, or lack of extent for the argon. And what we want to test is whether photoevaporation, one of these two wind scenarios, can explain these data. And we can do this by thinking about the launching radii, because as Naman mentioned, the photoevaporation cannot be effective as close to the star as the magnetically driven winds can. And also, if we can get information about the mass loss rate and the ionizing photons, that helps us also constrain a lot about the driving forces behind photoevaporation. So how are we going to do this? Well, we vary some pretty directly connected parameters. So there's the inner radius of the wind, which I'll often quote in astronomical units, but sometimes also in units of the gravitational radius, which is this kind of energetic length scale that photoevaporation has, which is what sets the inner limit at a fraction, maybe 10-20% of this Rg value. I'll also vary the density of the wind model, and this will be somewhat a proxy for the mass loss rate. And I'll also try a number of different spectra based on different studies in the literature. One that's been used in lots of previous photoevaporation models from Ercolano et al., and a couple from a paper that directly tried to model T-Chaz X-ray spectrum by Sacco et al. They've came up with 2 solutions, one with a lower X-ray luminosity and one with a higher X-ray luminosity. And then to test the importance of the extreme ultraviolets, the EUV photons, to those, I also add soft EUV components to both of those, up to the upper limit that is implied from the free emission. So the overall methodology of what I'll show here is that we start with a simple hydrodynamic model of the winds that we base on some self-similar solutions that I worked on during my PhD. We then pass this to a radiative transfer code, Moccasin, that calculates the temperature and ionization structure of the wind. And then we can also the line emissivities, and we can then take these in one of 2 directions. One is to calculate integrated line fluxes from those, do the kind of comparisons that Naman showed before. and the other is to try and create using MIRI-Sim, which is a MIRI simulator for the JWST instrument, detect images that I was then sending to Naman, and we were putting through the same pipeline analysis so that we could really try and compare them like for like with data. So these models that we use for the wind, these self-similar models, basically they prescribe the form of a streamline and the density and velocity profiles along it. I won't go into too much detail about that, but you can already see here that the temperature this model produces from the photoionization is pretty isothermal. And on the right here is the gas density of the wind with some critical densities highlighted. Now, what's Moccasin doing when we pass it this density model? Well, it's doing photoionization radiative transfer. So it has cross sections for all of the different species in the wind. And this results in the absorption of EUV and X-rays according to this black line. And this is what's going to attenuate them. So if we try and make an estimate for the column density of the wind, given typical values for an X-ray wind, we get something like 10 to the 20. And if we kind of compare that to here, we get somewhere around 200 electron volts will penetrate into a wind like this. Anything beyond that will penetrate, anything lower than that will be absorbed in the very inner parts. And we can see that that's quite close to one of the ionization thresholds for argon at about 250 electron volts. And you can see if we're in the vicinity of this part of the spectrum, neon and argon can be ionized at pretty similar rates by the X-ray, only a factor, maybe 3 difference. Whereas if we look at harder X-rays closer to 1 kilo electron volt, there's more than an order of magnitude difference because that's when we reach one of the neon ionization thresholds. And so we expect that perhaps the things that are most important for neon could be more penetrating. So here's an example of the outputs one gets from that with the electron densities, the ionization fractions, and then for the 4 lines that the man showed in the spectrum, the predicted emission, which is here mostly coming from inside the inner 10 AU, 50% even say in this model from inside 5 AU, but you can also see there's plenty of extended emission within this. So what can we do with this? Well, as I said, we can just take straightforward line fluxes from it, and we can try and compare them to some of the literature data. Now, I've been a bit more selective here, and I'm only showing literature measurements for disks where we know they're transition disks with low velocity neon winds. So up to the 10 to 15 kilometers the man mentioned before, where we know it's not a jet at hundreds of kilometers a second. And what we find is that if we compare the neon 3 to neon 2 ratios of all of these, of course, teachout is the only one for which we have argon 3 and can actually place it on the y-axis. They're all down in the bottom left corner somewhere here, or at least on the left of the plot. But if I look at the lowest density winds, the lowest mass loss rates, all of the model predictions are in the upper right of the plot. So this is no good. And as the man says, this rules out the entire wind being EUV ionized and essentially rules out, therefore, EUV-driven photoevaporation. So already just by these low ionization ratios, we require a high mass loss rate, maybe something like 10 to the minus 8 solar masses per year, which the man nicely pointed out is close to 1 lunar mass per year. And this is so we expect this to be something that results from X-ray photoevaporation. Okay, that was just the fluxes, but the ratios of the fluxes, but do the fluxes themselves match? Well, again, we can take the same sample. We see there's a little bit more scatter here now. Here's T-Chow's, the grey cross. And if we want to match the neon 2 and neon 3 line luminosities, if we do this in the slightly less dense model on the left, we tend to not produce bright enough neon 2. If we get closer, we have way too much neon 3. Whereas in these very dense models, we get somewhere closer. But also an important part of that is having a very luminous spectrum in the X-ray. So the more luminous version of the ones from Sacco et al. Gets us the closest to this cross. But you could still argue, well, I could take one of these models, and since the point size is the inner radius with a small inner radius and get close, or I could take one of these models with a large inner radius and get close. So how are we going to break this degeneracy? And the answer is to also use argon, because if we see that we compare the argon-2 and neon-2 fluxes, we get a value in one of these models very, very close to the observation for teacher, which suggested in a radius of about 0.1 of these gravitational radii, or about 1 AU for teacher. So what can we do going further? Well, okay, is a model like this going to match the line extents? Well, again, we can take some low density models. And if we just look at this before we do the actual synthetic imaging, just projecting these emissions that I previously showed in cross-section. On the left, we have the lower mass loss rates. And generally here, the neon-2 on the left and the argon-2 are just as extended as one another. Or maybe even the argon-2 is a bit more extended. Whereas on the other hand, if we go to the higher mass loss rates, again at the large inner radius, the two extents look very similar. But if we go to the smaller inner radius, it's actually looking promising. And this is the model that I said looked quite good from the luminosities. And this already looks quite promising for having more compact argon-2 than neon-2. But of course, this is very theoretical image. Can we actually see this in the observations? So we did a lot of work with this this MIRI sim and the pipeline to test this out. So on the right, you see the observed neon and argon, a bit like the images that the man showed, but before the PSF subtraction. And in the center, you see the simulated images. And qualitatively, the two look very similar. The simulated images are a bit fuzzier because MIRI sim perhaps doesn't quite perfectly match the PSF. But that looks generally good. You may be saying, okay, can we actually get any spatial information out of this? So what we did is fit a Gaussian to each of these images, which is highlighted in the green contour. And then the gray circle shows the same fit to the PSF. And these are very, very close in size, but it turns out there is a little bit of a residual. And if you sort of calculate this residual and overlay it on the unresolved model, you can see the argon-2 really is tracing rightly in a tiny, bright inner core within that, comfortably within that 5 AU where so the lines are brightest. Whereas the neon-2 is seeing a little bit more of the extended, and you can just make out that this green line isn't quite a point. And note that the scale here is several hundred AU on each axis, so this is quite consistent with that 10 AU scale I showed before. And we do this with some correlation matrices and trying to make an analytic estimate of the deconvolution. So okay, I've shown that for that promising model. Can other models fit as well? Well, if we take the inner radius and vary it from a small fraction of Rg to a larger fraction, we see that if we look at the very extended inner radii that would be probably outside the millimeter dust cavity that you saw in the ALMA image earlier, that actually we get a very extended emission that we'd measure. The size that we'd measure would actually be a pretty good measure of the wind's inner launch point, which tells us that these sizes we're fitting from the residuals really are telling us something physical. And but it would be way more extended than the observations suggest for teacher. So we can rule out that scenario that it's only coming in the outer disk. On the other hand, for smaller inner radii, this is not actually a great measure of the inner radius of the wind because you see these lines become very flat. Although, again, statistically speaking, the best fit probably is with this 0.1 Rg model when you include a dust cavity in the micron wavelength that's 15 AU in radius and allows you to see some of the backside of the wind. And the position angles we get out are very close to 90 degrees, which is sensible given that the wind is symmetrical and that we imply material must be being launched away from the disk if we have a wind. What about the argon? Well, the position angle here, you can see we derive huge error bars, which is telling us that essentially this is unresolved. And of course, therefore, the position angle is uninformative and not meaningful for a point source. But at small inner radii, the size that we are deriving is a little bit more meaningful because it is sensitive now because the wind is becoming more optically thick to the photons that ionize argon-2, which goes back to those cross sections that I showed before. And again, it looks like the most promising model compared to these sizes is the 15 AU desk cavity model with 0.1 RG in a radius, or 1 AU. And so we can see actually that all of these trends that we could see by eye in those images I showed for convolution, which we can sort of quantify by taking the radius containing a fixed fraction of the flux. Let's say we take the 50% radius here, and we see that for very large disks, the argon 2 might even be slightly more extended than the neon 2, whereas for small inner radii, that gets reversed. And we see that trend in the models after going through our simulation here as well. And again, the model which fits best neon 2 and argon 2 sizes is the same one with 1.3 AU. Now, this is significant because although RG is what scales this cutoff, it really is quite close to, as I said, about 10%. So this is really consistent with photoevaporation. And indeed, the line profiles are very broad, and these also come out, therefore, in support of a small inner radius, about 0.1 RG. So overall, we've ruled out EUV photoevaporation. We've come up with quite a high mass loss rate of a few times 10 to the minus 8, which implies a pretty dense wind. Now, this can be hard to achieve in some models, but given that we've also implied a very luminous X-ray spectrum, that's probably okay. Although one could maybe argue that magnetic fields tend to help assist the launch and could boost the mass loss rates there. And then combining the information from the neon and the argon, we were able to suggest that there has to be quite a small inner radius to get those fluxes and those relative sizes to match. And this is perhaps better evidence for photoevaporation, as there's no reason that the MHD winds would stop there. One puzzle that this perhaps raises then, and it leads on nicely into CY's final part of the talk, is that this means the mass loss rate we have derived from photoevaporation is higher than the accretion rate that the man showed on the slide earlier. And this is expected to be a short-lived phase, because once this happens, photoevaporation carves a gas cavity and the inner disk accretes. So maybe this is better explained by an MHD wind for this reason, but also perhaps we're seeing the disk during its final dispersal phase. So now I will hand over to CY for the last part of the talk.
Thank you, Andrew.
Thanks, Nama and Andrew, and thanks everyone for coming today. As you can see, my part of the work is more related to the overall spectrum, the continuum of the T-char spectrum, and it is not focusing on lines, but the overall feature of the continuum. And also, I'm going to focus more on the dust instead of winds and gas in T-char. So it might be different from previous two parts. And as we want to take a look at this kind of spectrum energy distribution, which we believe that this kind of SED is tightly related to the connected to the structure of the disk. Like if you see an infrared axis here, and you will assume you will think there is a disk around the star, and if you see this kind of dip in this kind of spectral energy distribution, it is indicating that the disk is gapped or it has a cavity inside. And the hot near shorter wavelength part is the emission from the inner disk, while the cooler one is more emission from the outer disk. And let's take a look again at the properties of T-char, which Nama has already showed it before, but I want to focus on three major things for me. The first thing is that there is a very large gap in the T-char. It is a transition disk, and we will see it later in the SED how it is shown. And also the disk inclination is around 70 degrees. This is a high inclination, but not completely edge on. And also, we noticed that the inner disk is very, very small. It is unresolved in this millimeter image. And here, this is the overview of all the previous data of T-chart spectrum plotted in as an SED. We can see you can see this large dip indicating that the large cavity, and this shorter part comes from the inner disk, while the longer part comes from the outer disk. And let's zoom in to this optical and mid-infrared part. We can see a very strong optical variability here, and around half of it is periodic with a period of 3 days, while part of it is random scattering. And this kind of optical variability is seen in both 1990s and 2018. This kind of optical variability is interpreted to be caused by the non-periodic part is caused by the occasional hotspot that you can see there are some excess above this kind of stellar photosphere. And the periodic part is believed to be caused by this inner disk occlusion. But we can see there's very little changes in mid-infrared bands before. All these points are taken before 2010, so no little mid-infrared variability before that time. But here, if we plot the JWST spectrum with them, we can see a very, very strong hand in the mid-infrared part. And you can see none of these points, photometry points taken before, is in line with the JWST SED. This is a very unexpected behavior, and currently we believe it is likely to be non-periodic. Otherwise, we will see some points in the middle of them. And how to reproduce this kind of mid-infrared variability? We have first, we have a classic model that a change in the inner disk wall height might contribute to this kind of seesaw-like behavior, that if we increase the inner disk wall, the wall height, and this will increase the near-infrared emission, but reduce the longer wavelength emission from the outer disk because it is blocking more radiation from the star to the outer disk. This way, we tried this way and we found that it can reproduce this mid-infrared seesaw behavior, this strong change. However, in this model, it is not possible to explain the optical variability, since we mentioned before that the optical variability, especially the periodic part, is caused by the inner disk occlusion. That's why we come up with a symmetric inner disk to reproduce this kind of both optical variability and mid-infrared change. To simplify our model, we just concentrate our all the mass into a very small region. This is very simplified, but we will talk about it later, how the physical meaning of, what's the physical meaning of it. And here, this is our model to fit both the Spitzer and the JWST SED. We can see that when we keep the scale height the same, by only decreasing the inner disk mass and this delta phi, that the optically thick part, we can reproduce this kind of seesaw behavior, mid-infrared change, while because we have a symmetric inner disk, when it is rotating, this SED at optical change a lot, while at longer wavelengths it also change a bit, which is also consistent with all the photometry points we saw before. And so for JWST, we have a new model that decreased in inner disk mass. Yeah, and how to explain our model? Our model is a very simplified model. And the first question is why the inner disk mass can decrease in such a short period. We believe that it is because the inner disk is already very low in mass. It is only 10 to the minus 11 solar mass. And we saw that the disk mass accretion rate is around 4 times 10 to the minus 9 solar mass per year. If we divide it by the gas to dust ratio, and we can see it is possible for the inner disk to decrease in mass in only 17 years, and with only accretion. And why we didn't see any significant change in the mid-infrared before, because previous modeling shows that there might be some other mass that be hidden behind the inner disk wall, do not contributing to the mid-infrared emission, but it is running out of this part of mass, and so the inner disk wall has decreased in mass, and a larger part of it is becoming optically thin. And this symmetric inner disk can be due to different mechanisms, including the accretional flows and something like a warped disk due to the inner disk material interaction with the stellar magnetic field. And also, a planet can be an explanation for this symmetric inner disk. Yeah, and we have also considered other possible explanations for this mid-infrared change. Some of them are periodic changes. It is possible, but not likely, since we have discussed it before that all the photometry points, they are quite consistent with the spatial data. If it is periodic, we should be seeing some points below that, but we didn't. But it is still possible that we are so periodic lucky that all the photometry points are taken in the same phase as the period. Yeah, and there are some other parameter changes that can reproduce this seesaw behavior. We identify that grain size distribution is possible because this mid-infrared emission is only sensitive to small grains. And other parameters we explored is not possible, and it is in the extra slides. If anyone is interested, you can ask about that. And here is our summary of my project. First, we discovered this kind of strong change in the mid-infrared spectrum. This change can be caused by this change indicates the inner disk emission decreased and the outer disk emission increased. And we believe a smoothly asymmetric disk that has changed in the past 70 years can explain both the mid-infrared changes for optical variability, and this kind of change suggests the inner disk is at its last stage of evolution. And here is the overall summary of the whole project. And thank you all for.
All right, thank you all three speakers. So with the first statements. And then this is the time for questions. So any question for any of those three speakers and their topics? In person here or online? Because I have a question. I don't know if I might have missed it. To teach out how hard or what is the luminosity, X-ray luminosity? I think Andrew mentioned that it's very strong, right, compared to the other similar type stars.
I know it's
And
high.
you're muted.
Andrew can probably give the exact number.
Andrew, you're muted. Yeah.
Trying to scroll, share screen, and unmute at the same time. Yes, it's fairly high. So Saka et al. Put a couple of different values on it. One was 4 times 10 to the 30, which is about twice the average for a solar mass star. Now, Teacher is more like 1.5 solar masses, and the luminosity tends to go up with mass. So maybe that's not exceptional. But then they had another one which was quite a bit higher. I think it is subject to some systematic uncertainty because because it's so highly inclined. They suggest one of the reasons they might get quite a high value is because of significant extinction from absorption in the disk. But so I think it's probably somewhere between these values would be reasonable. I
That's
mean,
order of
the exact
magnitude.
value they get out depends on the abundances they assume in the stellar plasma and so on.
So the X-ray varied more than order of magnitude.
It's not necessarily varying. These are taken from the same spectrum. It's just depending on the assumptions they make
I see.
to
It's
achieve the
same
luminosity,
spectrum.
they
Okay.
get nearly an order of magnitude difference in that. As I say, the high range of values could be high because there is a lot of extinction because it's quite close to edge on. So I think we don't really know exactly, but here, if you take the luminosities at face value, so here, I would suggest that in theory, this would probably have to be a little bit between the two luminosity values, which would seem reasonable.
Okay. I guess that I'll have a follow-up question later, but thank you. And I think John, would you like to unmute and ask question?
Yeah, great. Thanks for all the wonderful talks. I'm still trying to put everything together, but I wondered whether you might want to comment for each of the elements presented, whether the scenarios favor or disfavor the presence of a planet, carving out the transition, the optically thin part of the disk. I guess what I was thinking was for the wind, it seemed to be launched from within the optically thin region. Would we expect there to be a lot of gas there if a planet clears it out? Or maybe there isn't a planet there. And then with the changes in the spectral energy distribution and fluxes that CY explained, are those consistent with the planet or not?
Okay.
I think I'll go with the first part of your question of whether it is consistent with planets carving out the gap. And I think it is because the ALMA gas images of teacher do not show any gap in the disk and the gas disk itself. It extends out to 200 AU without any known gap in the gas disk. But now we know that there's this huge gap in the dust disk. And I think one way to explain this would actually rather be that the planet is carving out maybe this gap in the dust, and then now photoevaporation will probably do that to the gas. So yeah, that would be my answer to the first part.
Yeah, and for the second part of it, I'm from my part, we don't really need a planet to this behavior, but I would say we are not very sure whether there's a planet because we just focus on very inner part of the disk, and the magnetic field can already reproduce these things. So,
Thanks.
Okay, any other question? And I'd like to first remind it that one paper is going to appear tonight.
It has appeared in the journal
It's
today
in the
morning.
journal, yeah, this morning, and then Andrew's paper, it's being resubmitted, I guess, so you will see that soon as well. I'm kind of curious about the quantum connection, as just like what John mentioned. And the mass loss rate of the disk is higher than, I mean, the wind mass loss rate seems to be higher in this phase. It's a late stage, and then higher than accretion, which I'm not that surprised, but it's quite interesting to see that high wind mass loss rate. Right. How many systems do we know of obviously, or like, this is like what, 3, what is the accretion rate? Remind me, there's a 10 to the minus -9. So it's order of magnitude higher mass loss rate for the
yeah.
wind. Is it quite common, for instance, in chameleon or this kind of environment? I used to see this one. I think I'm used to it more in high UV environment, but not in T-char kind of environment.
Andrew, would you like to take that one?
Yes, obviously in the high UV environment, you have quite a different configuration because the wind is mostly coming from the disk's outer edge. And so you can get a very high mass loss rate while you're truncating the disk,
Right.
until perhaps the two equilibrate, and in a viscous model anyway, the accretion mass losses tends to be balanced roughly by the wind. In this case, yeah, this mass loss rate is achievable from photoevaporation. Certainly in the older models I've been working on, sort of the Owen et al. Models and so on. Now, not everybody agrees with these high mass loss rates, and I've been working on some radiation hydrodynamic models that bring the mass loss rates down. But given that high X-ray luminosity, I said it would be quite achievable, I think.
So
I
if
don't
we
think
have
many disks, though.
yeah, if we have more transition disk sample with this kind
Yeah,
of
yeah.
modeling
I
and
don't think
observation.
there are many disks for which we have this sort of estimate of the mass loss rate. There are probably some where you could try and just do it straight from line fluxes and things like that. But I'm not aware of anybody actually trying to systematically take all of those line fluxes and do that. I don't know how many in, say, Chameleon in particular we have, but definitely transition disks are a good target for that. The sample from Ilawi's paper. We have one other that was observed in the same program, and Naman is now doing all of that data reduction. So we should get to see at least one other comparison, and there's several other interesting sources that are in the GTO programs as well. So in due course, hopefully, I think we'll learn more.
Great, thank you. And
I don't
John,
know if Naman has anything to add about that.
yeah, thank you. John, would you like
Yeah,
to?
I had a quick question, Andrew. The really high mass loss rate that you mentioned and how it extinguishes the EUV and probably a significant fraction of the X-ray flux in the wind, pretty close into at relatively small radii. Does that suggest that, say, ALMA measurements of the gas in the outer disk would show relatively low ionization because the central ionization sources are extinguished close to the star? I just wonder whether the properties of the outer disk are consistent with this model, and whether you could prove that the wind really is this massive by showing that kind of the expected change in the outer disk ionization state.
Yes, that seems like a really good question. I don't know exactly which X-rays end up contributing the most in disk ionization at different levels. It's probably going to depend. You really need the very hard X-rays to even get to the midplane. So if it's something that's tracing the midplane of the disk, because there's just so much more gas in the disk than the wind, then maybe the wind is actually quite a small correction to what goes on in the disk. But maybe if you have something that's really tracing the surface ionization of the disk, um, uh, certain things like carbon lines, perhaps from carbon, if you can start seeing the CO dissociation or something, you produce the carbon, maybe you can start to see carbon ionization or something. It's maybe not so much in the X-rays though, more in the FUV. But yeah, maybe there's something to look for. I'd have to think more carefully about those gas tracers. I don't know exactly what gas data we have for teacher. I know there's CO data, which
Yeah, and then
the
sometimes people look at the ratios of CN to HCN or HCO plus or those kinds of
yes,
ions.
HCO plus seems the obvious one to go for me, but they'd have to speak to some of the experts about exactly where we expect it in the disk.
Okay, awesome. Thank you.
But thanks for the question.
All right, so last call for question here. 409. Okay, otherwise let's thank our wonderful 3 speakers, and I'll see you next week.
Thanks for coming, everyone.